This video is part of the membrane versus series, and this one deals with clarification processes and the key relationships governing their size. Starting with sedimentation. The rate at which a suspended particle in water moves relative to the surrounding water relates to its size and density compared with the water density according to Stokes Law. So particle gravitational separation, either through settlement if the particle is denser than water, or flotation if it's less dense, is promoted by large density differences and large particle sizes, the latter being a square relationship, which then increase the relative particle velocity. This increased velocity decreases the required retention time in the tank, permitting smaller tanks. The design parameter determining the retention time in a gravitational separational process is the surface overflow rate in meters per day, so it takes the same units as velocity. The SOR equates to the maximum flow rate at which the target gravitating particle is captured in the tank divided by the tank floor area. It theoretically equates to the particle gravitation velocity. So, if for a sedimentation tank there is some target particle of a certain density and size which is just retained before reaching the tank outlet, this implies that its settling velocity is marginally higher than the horizontal water flow velocity through the tank, resulting in the particle just being retained. For media filtration, removal takes place throughout the whole depth of the media. The gaps between the filter media grains must be larger than the particles which follow the fluid streamlines for filtering to be effective. The bigger the grains, the bigger the gaps and the faster the flow rate at a given pressure. This means that the filter cross-sectional area can be made smaller, though the grains must still be small enough and the bed sufficiently deep to limit breakthrough of the particles. So there's a balance to be had. The relationship between the pressure head H and the sand grain size is, in theory, given by the Cassini-Kármán equation. This equation indicates that H increases with bed depth and decreases with grain size and increasing bed porosity. The porosity actually decreases as the filter becomes loaded with particles during operation, requiring the filter to be periodically cleaned by backwashing. The key design parameter is the approach velocity, the volume flow per unit cross-sectional area, where the area approximates to the footprint. So it takes the same units as and is analogous to the SOR. The Cassini-Kármán equation isn't that accurate in practice, but does indicate which media properties influence hydraulic resistance. That's the resistance to flow at a given pressure. Which brings us finally to membrane filtration. The porous membrane processes of microfiltration and ultrafiltration reject particles which then form a deposit or cake layer on the membrane surface. This layer invariably has a much higher hydraulic resistance than the membrane on which it sits, and thus largely determines the throughput, analogous to the media filter. The cake layer formed during filtration has to be removed by periodic cleaning to maintain a reasonable flow. This is most commonly by backflushing, similar to media filter backwashing. The key parameter in membrane technology is the net flux in litres per square meter membrane area per hour. So flux has the same units as velocity. The membrane area depends on the packing density. That's the membrane area per unit module volume. So for a membrane process, the flow per unit footprint is given by the product of the net flux, packing density, and membrane module height. So, to summarize, the flow per unit footprint of a clarifier, media filter, and membrane filter can be respectively defined by these relationships. The first two being purely theoretical. The throughput for a sedimentation process depends on the particle settling velocity. For both filtration processes, is defined by the hydraulic resistance, the resistance of the filter to flow at the pressure applied. The filtration processes require periodic cleaning, whereas sedimentation is continuous. So, to increase the throughput or decrease the footprint, you need to either encourage the particle to settle faster if it's a sedimentation process, or decrease either the cleaning frequency or overall hydraulic resistance for a filter. And there are ways of doing all of those things.